All right, so today we're going to talk about Fieldbus, and we're going to start with this brief overview video from RealPars that is on D2L. All right, so the concept of Fieldbus, as we just kind of learned in that video, is it's not specifically one protocol or one this or one that. It's a kind of a group. It's more of a standard per se that like this is how it's going to function type of thing. And it's kind of weird to me that's like this is how it's going to function, but you can do this or you can do that. You know, it's not just one thing. All right, but it is something kind of interesting. So for a concept, this is a local area network for process control. This is not meant to go, running from building to building or anything like that. It's meant for local area, not very far. All right, this will be a two-wire signaling. So as you can see in this top picture, we've got our devices, and then we've got twisted pairs coming out of them, and this one, kind of jumps on the middle. So we do have multiple devices on there. All right, and why are we twisting again? Kind of. It helps reduce interference. All right, so by twisting them, it's kind of helping cancel them away down. So that's why we have them twisted. All right. So we are doing twisted wiring for this one. So this is just like Ethernet. It's got that twisting going on inside of it, except for this one's only 2 instead of 8 wires. Right. Now we have 2 wires for signaling. You still need your positive and your ground. All right, so still need some more of that, but kind of something just to think about. Up on the screen, that top right corner, that picture, I do have this mainly, I should say, to show you that at the top we've got our twisted pair, right? So our TP. Down here, why do we only have one line? Nope. Nope. Much simpler. Just to simplify drawing it. All right. So that is what's known as a one-line diagram in the world of electricity. Right? If you have a device A connecting to device B, and it's over a standard protocol or something, like okay, I'm not going to draw every single wire. The person reading this diagram, as long as I tell them that this is blank protocol or system, they should be able to go, okay, there are this many wires going in there. Right? A great example, another example I should say, is in the solar world. All of our diagrams for how things get wired together are one line. But it's like, oh, I've got 6 solar panels wired in series that have 2 wires and a ground, and then I've got 3 sets of those all in parallel. And I'm like, no, we're not sending, we're not going to draw 12 lines that go from point A to point B. We're just going to draw one line, and we're going to have some more information maybe somewhere just to tell you that it's 6 in parallel, 3 in series, or whatever the case is. And as the installer, I can look at this and go, oh, okay, I need to run these wires based on this information. It just simplifies the drawing. It's there to make it so when it's not, the dot drawing is also not like over full of information. You can imagine if you had like 24 wires on this. Why do we have so many? They all go from point A to point B. So we just call that a one-line diagram. All right. So that's really what's going on there. So, right, one line. One line. There we go. All right, now this can handle up to 32 different devices. Right? And my notes say that is 32 devices that are not bus powered. It means they're not all sharing the same power supply kind of way. Right? If you are going to have everything be bus powered, you're limited to 12. So something to think about. You also, if I say the word intrinsically safe, what does that mean? Right. These devices should not cause any problems. A great example of this is something in a room filled with explosive gases. You need intrinsically safe devices in there that aren't going to cause sparks and things like that cause those gases to go boom. All right, so that's what we say by intrinsically safe. So in that instance, we are allowed to have 6 of them be intrinsically safe. All right, so kind of interesting at that point. And then the last thing is repeaters are allowed. So that will help increase the length. It might also help increase the number of devices that can put on the bus. So a little bit of give and take in there. Repeaters, you think about again like the world of the internet and how we're connecting from here to California. We don't have one wire that goes from here to California without the signal changing happening in there. Or we're hitting a lot of routers along the way. Even if the longer lines with fiber optics, they also have repeaters on. So, repeaters are a necessity in the world of networking when we start getting the long distances. Like that. All right. So when it comes to our configuration, all right, we are going to have 2 power wires. All right, no surprise there. We are going to have 2 signal wires. Again, that twisted pair. We've already talked about that one. All right, and then there are lots of different ways that we can hook this up. So the first is we're going to have some sort of trunk. All right, so we've got our main trunk line kind of doing this. All right, so that would be our trunk line. All right, that's probably going to be slightly heavier gauge. Again, definitely going to be twisted, maybe a few other weird things about it, but that make it special to be a trunk line. All right, nothing too crazy going on there. All right. You also then could have drops or spurs. So each of these coming off of this would be our drop or spur. You got one there, you got one there, and then we got 4 going on up here. All right, nothing too crazy there. All right. Next, we need some sort of terminating resistors. All right. Anyone know why we need terminating resistors? And this will be kind of like consistent throughout all these most different network types. We need some sort of terminating resistor on them. Go, buddy. Not quite overflow, but it is, the whole goal is there to stop something. Right? The goal of the terminating resistors is to stop reflections. All right. Now, if you throw a ball and it hits that wall, what's it going to do? It's going to bounce and come back at me. All right. If we put something on there like a net or something that we throw the ball into, it's going to stop and stay there. All right. We don't want these reflections coming back down the line. And the same thing does happen with electrical signals. There's energy there, right? We're transmitting the signal. It's going out. It's going to hit something. It's going to come back. All right. And that just causes more interference and weird things happening on our buses. So we want to help limit that. So we're going to have terminating resistors. Now, depending on the system that we're using, the terminating resistors are going to change. Right? Profibus may say we need 100 ohm. Another one may say we need 125 ohm or 120 ohm. And we normally, or you should, have terminating resistors on both ends of the trunk. At the very beginning, you should have a terminating resistor. At the very end. And what that terminating resistor does is it basically makes the wire feel like, according to the electrical signals, like it's infinitely long. So the signals hit that terminating resistor and they kind of technically like burn up. I mean, they become heat. They're burning up. So that's what's happening with those terminating resistors or those terminators. We do have a communication rate of roughly 31.25 kilobits per second. We got a pretty quick, all right? That would be, what, 312,000 basically bits per second. So that's faster than most of the serial that we've talked about so far. Your response times will be anywhere between 32 microseconds. Let me write that one out. 32 microseconds and 2.2 milliseconds. All right. Now, how do we go from micro to milli? Anyone remember? On the direction. All right. So, quick little, if we've got our base unit here, whatever it is, all right, and we've got our prefixes. So you have UD base, then it would be milli, then micro, and then nano, pico, yada, yada, yada. And if it would go up, it'd be kilo, mega, giga, tera. Tera's next. Tera. All right. And each of these is plus 3 zeros or minus 3 zeros. So from base going up, it's be plus 3 zeros. Going down, it would be minus 3 zeros. All right. So if we're going from micro to millo, we're moving up, which means we're adding 3 zeros to that, or actual, kind of. All right, we're actually, in this case, we are taking 3 zeros away. So if this is our period right there, 32 microseconds, we would move the decimal to the left 3 times. That'd be 0.032 milliseconds. 2.2 milliseconds. So that's a pretty big range in the long run. All right. So just kind of some information for you. The length of the spurs, these drops that we're doing, all right, that's going to depend on the type of wire you use and the number of spurs. All right. So how long can those be? Well, you only get 20 meters of spurs, or something along those lines. All right, so if you have 4 that are 15 meters long each, you're already screwed. You're already way too long according to the specification. Now, again, different communication protocols may have some different specs there, so there are going to be some tweaks to this. But again, as I said, Fieldbus is a group of other protocols. There are a group of other kind of specifications. Not a great term. Best protocols on their own. So I just want to say this is all going to be taken with a bit of a grain of salt. First. All right. Terminating resistors, they're still going to be there. Spurs are still going to be allowed, but maybe the max distance will change or something along those lines. So, all right. So we do have the host. All right. As you can see up here, we have one host. All right. We also have a power supply, and then we also have a power conditioner. All right. But the host, that is going to be kind of the in the older terms, I'd call it the master device. All right. That's the one who's leading this parade, wherever the parade's going. All right. So he is the one that is going to oversee all of the operations on this network. That would be like the router in the world of Ethernet. Now, one of the jobs of that host is for link active scheduling, LAS. All right, and this is going to control access to the bus by granting permission to each device according to a predefined schedule type of thing. All right, be probably time-based, like, okay, you got it for 5 milliseconds, and you get it for 5, yada, 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 or it could be, okay, you're done talking, who's next? Type of thing. So we're kind of moving around the game here. All right. No one can talk on the network without having permission from the LAS. So, again, not really surprising there. You need to kind of add, like, hey, can I talk? Yeah, oh, cool, it's my turn, great. All right. And there, as I said, there's two types of schedules. There is that periodic routine, so it's like, okay, it's Chris's turn, then it's Dylan's turn, then it's Braden's turn, and we just kind of circle that. There is also a non-periodic routine, right? Don't ask me how that one works. Just know that there is an option for non-periodic or acyclic. All right, so this is going to be more unscheduled type of thing. All right. Yep, and so what we're also talking about here with the cyclic and acyclic is things reporting information. A sensor could be reporting some information consistently. Okay, every 1 second or half a second, whatever my time is, I'm reporting information. That would be a cyclic. Where maybe you have a VFD where it's like, I am sending you information, you're responding to me. That would be an acyclic. Not always going to be transferring information. All right. And then last year, we've got a publish and a subscribe method. What do you think that means? All right. So basically, right? If we think about this in the wonderful world of emails, right? You get emails from all these lovely people that you are subscribed to. That one in air quotes, right? You subscribe to all these lovely emails you're getting, all right? You are on their subscription list. So that means they send you the email when they send it out. They are the publishers of the information. So they're sending information out. You're subscribed, so you're like, oh, cool, I got this email. Great. All right. Same idea is happening here. Everyone's just publishing their information on the network. And all the groups get to decide, hey, yeah, I want that information, or no, I don't actually need that information. They basically ignore it. All right. So publish and subscriber. So it's who actually cares, like, take that information and all right, so we have signaling on this, all right? And how they're signaling is by varying the current draw, all right? With serial, we were doing voltage, right? Now we're going to be doing current, a little bit different, all right? So we can either push or pull 10 milliamps, all right? Now, if you think about that, if you're pulling milliamps, you're also changing your voltage. So it's not technically, are we measuring voltage or are we measuring current? It's like, well, technically, we're probably measuring both, all right? If you actually think about your standard multimeter, that is actually only ever measuring voltage. Even though it does current, it does distance, it does all these things. It's really only ever measuring voltage. And it's using Ohm's law to do that. It's like, okay, you want to measure a resistor. It's like, okay, I know I am going to supply 5 volts at 10 milliamps or whatever the magic that multimeter is using. And it measures the voltage drop across that resistor. And it's enabled to do the math to say, oh, if the voltage drop at 10 milliamps is this, that means the current is, or the resistance is this, and it shows you on that screen. So it's only ever measuring voltage. Same thing with resistance. It goes, okay, we're pulling the resistance drop across this resistor with a known value of 0.002 ohms or whatever the magic value is this. We know the resistor value. We know we're pulling. Yeah, the voltage is this. We can now calculate the current. All right, so it's only ever measuring voltage. So a little bit of give and take going on. All right, so we're pushing and pulling 10 milliamps. Again, that 31.25 kilobits per second is up there. All right, we do have a preamble. Anyone heard of a preamble before? No. All right. Vaguely. Any idea any way to describe it? Excellent. All right. Something before something else. All right. So in this case, the preamble would be alternating zeros and ones. So just 1 0 1 0 1 0 1 0 1 0. And part of that is to let everybody sync up on the network. Again, we talked about serial, we talked about synchronous versus asynchronous and the whole clock thing. Well, if there's no clock signal for everyone to follow, you have to know how fast they're sending information. So by sending a preamble out of 0 1 0 1 0 1, you're now able to say, okay, hey guys, here's my clock cycle. Here's what it is. Click, 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 based on those zeros and ones. So everyone can now know how to decode your information. Now, how long that preamble is, well, that's going to change a little bit. It could be 2 0 1s, or it could be 20 of them. It really depends on your personal preference there. Right? It could be time-based. Okay, we're going to send 5 milliseconds preamble out first. You don't want to send too much preamble. Why? Exactly. Right. If I send out 1 minute's worth of preamble before I send every message out, right? Like, well, exactly. You're like, well, there's now 1 minute of no data that I can send. Right. So you want enough preamble to get everything synchronized, but you don't want too much. I'm assuming you don't get to choose how much preamble you have. I think it's just kind of like set, but it is going to be there to help get everyone synchronized and things like that. All right. We also then have our start delimiter, our data, and then our end delimiter. So we're going to be going, kind of through this. All right. So our preamble, so maybe that would go to like here. That would be our preamble. You can see it's very consistent basically through there. Then maybe we'd have our start, all of our data, and then our end again, right? Just kind of like serial. And it's just like, oh, we've got our start bit, we've got our data, we've got our parity, and our stop bit, right? Same idea going on here. It's just slightly different, right? We have FCS. And take like a random guess here. Yeah, I didn't think so. Frame check sequence. Right, so this would be like our parity in the world of serial. Right, so this is used for what then? What's the point of parity? Guys aren't giving much hope for your test. Point of parity is for error detection. Frame check sequence is also for error checking, right? So this makes Fieldbus much more robust than any other network type or other control network. Anything that's going to have error checking, it's going to be a bit more robust than the ones that don't. Should be pretty obvious, right? And then back to our LAS for our link active scheduler. All right. Now, this is where we start and get into me a little on the weird side. All right. So we have 4 different options here, according to our encoding rules. You have a 1, which is a high to a low transition, so that would be right here. We have a 0, which is our low to high. You also have an N+, which is non-data plus, which just keeps it positive. And then you have a non-data minus, which just keeps it negative. Really weird to me. I don't know about you guys having these 4 different. But that's what they do. So here you can see the start delimiter and the end delimiter. So we've got, our 1, N+, N-, and you would think, and so this is, you would think it'd be like 1, N+, and then there would have to be a 0 or something, right? Because we're transitioning, but no, it's talking about over the width of this, our signaling time. All right, so we have to take that into account. So if this is my signaling time, for when they are. You can say, oh, this one transition, that's a 1, this one didn't, and it's positive, so that's an N+, this one didn't, and it's negative, now it's an N-. Oh, transition again, now we're at a 1. to me really freaking weird. But that's just how this game works. Questions on the N's, pluses, and the minuses, and the... You're like, not right now, but don't bite me in the butt, probably. All right. Anyway, our cable. Shielded twisted pair is ideally what we're going to use. All right. So you can see we've got our twisted pair going in there. We've got our red and our black. All right. And we've got some foil going around it. And then we've got a shield drain wire on top of that. There's a lot. Could you get away with non-shielded twisted pair? Maybe. Right. It's the lovely world of the environment that you're in. And your goal here is probably to protect your networking as much as possible, to have as little interference as possible. You probably don't want to go unshielded very long. So you do want to take that into account when you are buying wire and things like that. One of the best things I can tell you guys when you get jobs in the future, if you can, convince your boss to have everything on hand possible. Yeah, we need to spool this wire 200 feet. Why? Well, if we need to repair something. You know, it's so much nicer to have it on hand ready to be used than going, boss, the network's down, I need this wire, we don't have it. All right, so you want to have as much resources on hand as you possibly can to fix whatever possible problems are going to come along. So you can buy extra wire, buy extra connectors, whatever the case is. I've got all sorts of like pneumatic fittings. So that way, when I'm working on my robotics or PLCs, I use pneumatic fittings. I don't have to go order them, and it take 2 weeks for me to get them because the ordering system, screw it. It's like, no, I go to my cart and I use them, and as I start realizing I'm getting low, I'm like, I better reorder these things, right? So those types of things, highly suggested to you. Keep the small things, especially if they're cheap. They're like $10, boss. We just buy a bag and buy something like every week. My other, don't be like, yeah, here's 30 grand worth of supplies I need. Be like, no, I need $1,000 worth of stuff to, keep our inventory up. Like every week or two, put a little order in. And as your boss gets mad at you about all your expensive orders, just reduce the custom. Here's a $10 order. Just kind of keep going as much as you can. All right. So cable, shield, twisted pair, suggested characteristics. That shielding should be 90% coverage. All right. All right, so, whatever your length of the wire is, obviously right here is not covered. 90% coverage would be good. And the impedance we're looking for is 100 ohms plus or minus 20% at this specific frequency. All right. Anyone know what the hell I mean by any of that? No, exactly. All right. Ohms, you probably, hopefully all have heard something about. What does ohms normally relate to? Resistance. All right. Now, as we are putting frequency through things, the impedance gets kind of weird. It's not consistent. All right. If you're just drawing power through it consistently, pulling an amp or whatnot, you're going to have so much resistance on that wire. Anytime you're starting to send frequencies down that wire, resistance, or in this case, we're now dealing with impedance, is going to be changing. All right. So at 31.25 kilohertz, you want to find impedance that is roughly 100 ohms. Now, plus or minus 20%, that means we could go down to as low as 80 or up to as high as 120. All right, so that is definitely something that you want to kind of keep in the back of your mind. Good cable manufacturers will be able to tell you this information. Cable manufacturers might not be able to tell you this information. All right. And I don't remember, I don't know if this is 100 ohms per 100 feet, or what the magic. So I need to look that. All right. Now we have 4 different types of wires that are traditionally used with Fieldbus. You have type A wire, which is 18 American wire gauge. All right. And that can go up to 6,232 feet. That's a lot of distance. All right. You have type B wiring, which is going to be a little bit smaller. That's going to be 22 American wire gauge. All right. Or 2,936 feet. So nowhere near as long. All right. We're only about half. All right. You have type C wiring, which is 26 American wire gauge, and that can go up to 1,322 feet. All right. Now this is the one that always screws with me. Type D, which is larger, 816 American wire gauge, is 660 feet. Now, I don't know what the special about type D. I should look that up too. Or my note could be wrong. I'm sticking with my note until something. But I'm pretty sure I pulled that right out of the reference. Everything. It's kind of something to think about. Yeah. All right, moving on. The terminator. We already really talked about this, but we need to have a terminator required at each end. Without the two terminators, you're going to have improper signals because of stuff reflecting and all sorts of other nonsense happening. So we really need to make sure we do have those terminators. If something is funky happening on your network and you're like, what's going on here? Check your terminators. Make sure they are there. All right. I have this note here that says it may be part of your power supply. All right. That's all well and good. Built right in my power supply. I don't have to worry about it on the one cent. Awesome, right? Until your power supply goes out and you replace it. And then you forget that the new power supply, or you didn't check the power supply to see if it has a terminating resistor in it. So all of a sudden, now your network's acting funny. You're like, what the hell? The power supply went out. I replaced it. Why are we acting funny now? You lost your terminating resistor. Right? So definitely something that you want to be extra kind of cautious of. My notes do say that if you only have one, it may appear to function properly, but it's going to have distorted signals, and it will increase their amplitude and greater susceptibility to signal reflection noise. So really make sure you have both. All right, my notes do say here that we're going to have a 100 ohm resistor. That is what the magic notes say. All right, so if I've got my lovely Fieldbus going on here, I've got my resistors at my end here. How do I check if my resistors are actually correct? As quick as possible. What test would you do? Well, if the resistors are there, and so like my network's not acting correct. Just replace the power supply. Okay, how are we going to check this? All right, the simplest way, well, I mean, what you could do is, right, you could unhook a resistor, check out one, plug it back in, go find the other one, or check the power supply, see if it has one, right? The other option is you could just test the wires, right? You can just go probe with my voltmeter in ohm mode. All right, now, if we're doing that, what resistance should we see? Not 100 ohms. Not 200 ohms. Not a bad guess. We got two resistors, right? You're like, it's going to be 200. 150. Getting closer. You guys must not have done resistors yet in the early 110. That's fine. Okay, what did you say? 50. Ding, 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 ding. All right. Wonderful world of resistors. If you put two resistors in series, resistor in series. All right, it's R1 plus R2. All right, plus R3, you just keep adding them up. If they're in parallel, I'm just going to break P for that. It is 1 over R1 plus R2. No, it's 1 over 1 over. You add them together and you divide by 2, or you divide it. But yeah. That probably will also work. But I think it's 1 over 1 over. Yeah, I think it's 1 over 1 over. Let's quick test this. Yes, it's 1 over 1 over all R's. Right, and so we could keep going. Let me fix that in the background here. So it's 1 over R plus 1 over R2 plus 1 over R3, till infinity. Right? So it's really simple. So you should see 50 ohms there. Right? So if there was 120 ohm resistors as you're terminating, what would the value be? $60. Yes. All right, quick hint for you guys. If you have two resistors in parallel and they're the exact same one, you just divide it by 2. Real simple. All right. Yeah. So could we do this in series? Yeah. If we were to like cut this wire or unscrew it from the one resistor, you could put your ones there. We cut the wires, unscrewed it. We had the other one there. Then we would see 200. All right. But the benefit of doing it in parallel is you just go to any device where you've got screw terminals. And you just poke your leads on, and you're done. Right. So that's why the parallel option is going to be the better one. All right. We also would do a quarter. This only needs to be a 1/4 watt resistor. We don't need a lot of power here. right? This is just dealing with signaling. It's just, you know, little pulses. Quarter watt's going to be plenty. That's going to be, I'm going to say, your standard through-hole resistor size. All right, I'm not saying you should just go to your resistor drawer at home because you need a quarter watt 100 ohm resistor, grab one and go shove it on your network. But technically it would work. And then the last thing, you might also have a capacitor that's sized to pass 31.25 kilohertz. All right. This is not something that you guys have gotten into yet, but that is called a resistor capacitor circuit, an RC circuit, and that is used for filtering. Right, so maybe we will come back to that one at some point. All right, let's move it on. So wire connectors. So here we have a very nice little terminal block. All right, you've just got some screw terminals going on. Your life is really easy. Internally, these little, you know, these are connected together. These are connected, you know, yada, yada, yada. So you put your positive in, positive can come out, signal plus, signal minus, you know, whatever. And then we've got little jumpers that come down to the bottoms. Just erase this because they're already there. We've got our little jumpers there to come down to the bottom, so we can then trunk off of this. Great little system. Anyone see any problems with that? Two potential problems. One, on this right here, we've got two wires. We've got the wire going out and the wire that's jumping us down to the other section. All right, not really the end of the world, but we do have two wires there. So that could be a problem area for you. The other problem is it's very easy when you're doing this to get screwed up and switch your plus and your minus or something like that. So all of a sudden now your signaling is inverted or, you know, whatever the case is. All right. So very possible problematic. All right. So it works, gets the job done. There's really nothing wrong with it. You just have to be a little bit more careful when you're using this type of system. Option B would be something more like this. All right. So we've got our trunk wire come in, and then we've got this little distribution box, which splits it out into 9 different connections. And then again, like this would be your trunk going out the end, which goes into another distribution box. And we have our trunk here coming out, you know, to the end of the terminating resistor. Right? So this one, all of the jumpers are internally built into itself. So you can't screw up the positive and the negative internally, at least, those little jumper wires. What you can do is when you're making your connectors onto this, you know, if you have a specialty connector that you're just plugging in, if you have little screw terminals on them, that you could definitely screw up. So here we've got a nice little connector, right? You know, you can't, it's all keyed and whatnot, so you can't plug it in backwards. All right. It does even have, I thought it had, yeah, it's on the bottom one. You've got colors there, so you know, oh, red wire goes here, white wire, you know, yada, yada, yada. So you're less likely to screw this up, but it is still completely possible. And these are actually kind of nice because they actually have 2 spots for wires. So they're internally connected. So as long as you know, this could just plug right into one of these things. Now this is for device net. This is not for Fieldbus, but just as a nice little example of a connector going on. Right? So that does make your life a little bit easier having, you know, this type of connector. Can you still screw it up? Yes. Are you as likely to? No, you're not as likely to screw it up. All right, I had one other thing I was going to say, just don't remember what it was, but yeah. All right, and we were talking about terminating resistors. Well, here would be an industrial terminating resistor. Right? This one was made in Japan, but that is all this is. I don't know what the value is, but that would be a possible terminating resistor there. This is why I say you don't want to just go grab your little quarter watt resistor and shove it in. Technically, it would work. This is much more, I'm going to call it industrial, right? It's got little screw terminals on it. You got a place to put the wires into it. Everything's all kind of a bit better with this type of thing. Is it going to cost you an arm and a leg? You damn well better believe. But it's going to be probably a better answer for your industrial application. All right, and that is one of those things that comes down to a lot of this stuff. You can DIY, like basically anything we're doing in this world of industry, right? It's like, oh yeah, I could buy this PLC for $1,000, or I could buy an Arduino for $20 and build the same thing for 1/3 the price. Yes, you can. But A, is that Arduino hardened for the industrial environment? The one you're thinking for really cheap? No, it is not. All right. B, when something goes wrong, it's now up to you to fix it because you're the one that made this custom solution for the problem instead of going to industrial solution where more people are likely to be able to fix the problem. So a little bit of give and take going on there when it comes to industrial equipment. All right, moving on. So when it comes to power, all right, this does say that a power conditioner is required. All right, and the whole point of that power conditioner is to help to absorb those signals. So that way we don't have weird signaling coming into the power supply or coming out of the power supply. All right, if you think about it, most power supplies nowadays, anyone know what they're called? SNPS. Most power supplies are switch mode power supplies nowadays, which means we take the AC in, rectify it to DC, so we have a high voltage DC. We now pulse it at a very high frequency through a transformer. And why do we have to pulse that DC? Well, because we want to go through a transformer. Why do we have to rectify it first if we're going through a transformer? Because the higher the frequency, the smaller the transformer. All right? So we pulse it at a very high frequency through a transformer, which drops that voltage down to a more acceptable level, and then we smooth it and everything out. But that means we have this high frequency pulsing signal happening in this power supply. Okay? This little one that I had, this is a 5 volt, 800 milliamp power supply. So that is a switch mode power supply in there. All right. You actually go to like an old school one of these, you have a transformer that's probably about that big and weighs about a pound or whatever, compared to these little power supplies that we have nowadays. And they're only getting smaller. I don't know if you guys have realized that. It's like, oh, yeah, that's a 50-watt power supply, and it's the size of this thing nowadays. It's like, holy crap. Right? This is like a 4-watt power supply. 5 watts, 5 volts, 800 milliamps. So yeah, 4 watts. So we're coming a long way with power supplies. So those switch mode power supplies, they're great. They're small, they're compact, and they're very energy efficient. All right. The downside is we have this high frequency pulsing happening, which, if not properly filtered and capacitor to smooth and all those other things, is going to cause problems. All right. Fun little side note here for those who don't know how power supplies work. You take your AC in, and then we rectify it. All right. And by rectifying it, we take our AC and it looks like that, and it now becomes pulsating DC. So it's now doing this. All right. So it's all on one side. Then you throw a capacitor on that, and it does this. All right. So we never make it back down to 0 because we charge that capacitor up to full, and then as the AC that's bouncing goes down to 0, that capacitor is draining, and then that AC comes back up, fills the capacitor back up, and does it again. All right. So no matter how big of a capacitor you put on an AC power supply, it is still always going to be a little wiggly. It is never going to be perfectly flat. Okay? And the world of industrial applications for like PLCs and robotics and laptops and phones and things like that, that's fine. But if you have an instrument that requires a very, very, very steady power supply, your only option is batteries. So if batteries aren't doing this draining and getting charged back up constantly, they have a much larger gas tank, so they're just a much slower, consistent decline. All right. So, but there are some devices out there that require batteries because of that very consistent voltage that it needs. Any little fluctuation is going to cause your output, your temperature readings or whatever, to fluctuate as well. So kind of a fun one. But anyway, so power conditioning, going to need it for absorbing signals. Traditionally, this is going to be 9 volts to 32 volts. All right, as I told you guys, I think before, roughly the magical world of 30 volts is where we start qualifying DC as being less safe. All right, because now your resistance of your skin might not be high enough to avoid having the shocks come through. All right, I think it's actually a bit higher than 30 volts, but 30 volts is always what I was told was the acceptable. So what I keep telling people. Generally, 24 volts is what we're going to use because that's what we just like. It's a nice consistent voltage. You would think they'd want to go like all up to 30, and I agree with you, but we seem to like the things in the world of 12 volt increments, 6 or 12 volt increments when it comes to most industrial. And I think that's just because of the world of car batteries. Started with 12 volts, and people are like, oh, okay, we can do 6 volt, 6, 12, that way you can kind of go to 18. Or I think that's why we're at 24. A high enough voltage that we can drop our current down. Now, they do suggest 320 milliamps, and I have why here, but I haven't had you guys read the book yet, so you're not going to have any freaking clue. And the key here is most of these devices are going to be can pull up to 20 milliamps. All right. And if we go back to like one of the earlier slides, you remember that I said you can have 16 devices on a power network. 16 times 20 milliamps is 320 milliamps. All right. So, and That's not a lot of power. All right, that would be 0.32 amps. All right, so it's not like, oh, we're pulling a lot of power on this network. No. All right, we have a very low power supply here is really what it's down to. We want to avoid having a common ground. All right, and that is to help reduce the noise from other equipment. Now, common ground is not the negative on the battery. All right? Very often, you'll hear me and probably other people say negative and common, ground, same thing, right? You're like, oh, you connect that to ground. Oh, negative and ground are technically not the same thing. All right, so we need to make sure we keep those separate in the long run. I have a hard time with this myself. I know I screw it up. Anytime I talk about the world DC, it's like, yeah, that's the ground connection. It's like negative. I don't know why I've just gotten ground stuck in my head over my something I really need to fix. All right, so we do have that. Now you can have a redundant power supply with this type of system. 100% allowed. No real issues with that. All right. So it is something that is there, and you might want to do for the purposes of reliability. All right. So we want to keep reliability of these systems as high as possible. When you get into the wonderful world of anything industrial, every downtime could, like 10 seconds of downtime could cost the company hundreds or thousands of dollars. You think about it, you're like, oh, we produce, one item an hour or whatever. It's like, okay, so we cost the company, 2 products or, whatever, however many products that we make. Like, well, yes, but no. By being down for so long, we now had to pay all these employees to sit here. We didn't make that product, so we're not making the money back. We also now missed our deadline, so that's now costing us an extra this, or we now have to do overtime. It's, you're like, oh, little downtime is not the end of the world. It's like, well, if it's not planned downtime, yeah, it can very much cost the company thousands of dollars to be down for very small amounts of time. Right? So we may want to have some backup devices for reliability purposes. So we can have a backup control device. So the master that's doing the link scheduling and things like that. You want to have spur circuits that have limiters between the trunk and the spur. So this will help protect against shorts. Because if the spur has a short circuit on it, that you don't want to take down the entire network. You'd rather just take down that one little spur of the network, so at least some things can still be operating. So we want to do that. That could be built into those lovely junction boxes that we saw a few slides ago, right here. You could have a little limiting resistor basically on every one of these spur boxes. So that way you are resisting that possible downtime from crashing the whole freaking network. Also, depending on how your power supply is built, if you have a short circuit, that could destroy your power supply. Hopefully, you have fuses in place to protect your power supply from that type of event. Or your power supply is smart enough to go into a fault mode when it detects too much current. So that way you just have to power cycle it and it will come right back on. Or, even better, it just keeps checking and goes, nope, fault's still there, fault's still there, fault's still there, and then finally when the fault's gone, and it automatically brings itself back up. Right? Downside of that is it's not the best on a power supply if you have a consistent fault for it to be constantly checking, because it's now just like, overheating components constantly. So, how do we protect against trunk failures? Our main trunk line. Probably not something that we can have a backup trunk line. All right. Any other options? How would you physically protect the trunk line? Oh, physically protect it, right? I don't want to be able to have an axe or a wheel or something hit this wire. So we could run it in conduit, armored cable, something along those lines. Yeah, this is not like, oh, we're going to do something electrically fancy here. No, this is like, put it in armor, protect the thing, right? Now, this obviously is not always going to be possible to have conduit running everywhere, because if you have something that's moving that has that trunk line that needs to get to it, you can't protect it with conduit. So that's where the armored electrical cabling come in. So you could protect it with something like that. Still not the best thing in the world, in my opinion, to have this armored cable flexing constantly. But any wires that are flexing constantly is also just a failure point over time. If you take a wire and just bend it back and forth a whole bunch, you're stressing at that same spot, it's going to. Now having a nice big loop, so you're not stressing at one specific point, you're stressing it over an entire arc, going to be better, but still something we need to think about. Power supply failures, we've already had that. We've already talked about that. You can redundant. Now, anytime you do have redundant things like power supplies or stuff like that, you need to be informed when the primary one goes down. Why? Imagine you have two generators at your house, and the one's an automatic failover. So once the first one fails, the backup one kicks on. And sometimes the first one will start back up fine, you know, everything's all hunky-dory. But one day, the main one just stopped working, running off your backup generator, and no one ever told you the main generator died. What happens when your backup dies? You're out of luck, right? Well, same thing here. It's like, oh yeah, we got redundant power supplies, we're good. Like, yes, as long as you know your main one's dead, because then you need to know you need to replace the main one, right? So you do want to make sure that something informs you when your main one goes down. Some companies will set power supplies up or pumps or things like that that you have redundant of, a backup of for emergency situations like that, but they'll actually alternate between the two. And it does two things for you. One, it wears them evenly, so you don't have one that has 10,000 hours on it and one that has 1 hour on it. It also allows you to constantly be checking your backup to make sure it is working. So if it's able to switch back and forth between them, make sure, yeah, our backup system's working, we're fine. It just gives you peace of mind. So that's the benefit of wanting to test your backups kind of regularly. All right. And then the last thing we want to protect against for reliability purposes is surges. Right. Electrical surges is something you're going to see, right? Especially in industrial environments where you've got like 20, 40, 50 horsepower motors starting. There's going to be a voltage drop when that happens, and then when they turn off, there might be a voltage spike. All right. There is industrial application is extremely noisy when it comes to the world of electrical because of the power draws. Like, turn the motors on, turn the motors off, especially if you're not using a VFD or something to soft start motor. Right? So soft start means we're gonna like ramp it up to full power, not just be like contactor clunk. Full power just surges right to that motor. Motor is basically a dead short. If you think about it, right? It's just a wire that wraps around a whole bunch of things and comes back. So when you turn a motor on, it's got a dead short. It's like, oh man, we can flow all this power this way. That means all of it's going this way and not as much of it's going to go this way now. So a little bit of give and take going on. So definitely something we want to think about when it comes to that for surges. We also have lightning, right? You want to have nice lightning protection around you to make sure that everything's not going to crash and burn. So we have surge protection and things like that to help protect against capabilities. And there's multiple ways to do surge protection. You can do surge protection on a specific device. You all have power strips that have surge protectors built into them. You could also do surge protector for your entire house or building and have one giant surge protector somewhere, right out here, and the power coming in to help condition it that way. Not going to say one's better than the other. One thing I will tell you all is surge protectors have a limited life. Right? They're not good forever. So you also might want to just like replace your surge protectors at home. Something to kind of think about. And then here we've just got a little Fieldbus segment going on. So we've got some home runs, we've got some spurs. Yeah. Balanced transmission line. Other thing I'll say to you guys, my notes say you can't run 2 home runs and use them both for redundancy. That is 100% true. What you can do is run 2 wires and only use one of them and have a backup wire pre-run. If you think about it, right, you're running wire through conduit or over all this stuff from point A to point B in a building. Whether you want 1 wire or 2, does it cost you any more in time? Probably not much. All right. What it does cost you more is cabling, right? So if you've got to run conduit from point A to point B and you're like, man, it's going to take me 4 hours to do that. It's like, well, 4 hours at $50 an hour, that's $200 or, it's going to cost you to run it. It's like, I got to run, $50 worth of cable. It's like, okay, I got $250 now. Do I run a second cable now for an extra $50? Now I have $300 into this project. Or do I do it again and have $500 in the project in a year or two? Probably better off running that extra cable now if you can. All right. And this is something that I did at my house. I ran an Ethernet cable from my basement all the way up to my attic. Why? I don't know. I have no need currently to actually have an Ethernet cable in my attic. But I was putting insulation in my attic and whatnot, so I don't want to have to go tromping through that. So I did it for future proofing. So if in the future I want to put an access point or a weather station or have an HVAC system that has an Ethernet port on it that I can plug in, the wiring is already run. I'm done. I don't have to think about running another one. All right. So it just saves me a lot of time in that aspect. It costs me a little bit of Ethernet cable. but it was cheap enough to do ahead of time. So I like to future proof when I can, what it comes down to. We talked about not grounding things, so you only want to have the ground connected at the power conditioner. Yeah, okay. This does say also a standard power supply cannot be used to power a Fieldbus segment. All right, and that's because of its low internal impedance. So again, I have some specialty equipment going on here. So just something to think about when you're playing with anything for networking. And I hate it. I am the first to be like, why do I need to spend $1,200 on a power supply? I can buy a 5-volt, 200 amp power, 100 amp power supply, whatever, for that much money. Why am I buying that much for a 300 milliamp power supply? First one to say it. But sometimes there are reasons. And like, make sure it's certified for Fieldbus. It's going to be one of those. All right. Any major questions on Fieldbus? All right. Well, that would be the lovely end of this presentation.